Okay, chapter 3, I don't know if you have looked yet, but if you look at the assignment sheet, it's maybe 4, 5, 6 days, 6 days long. It's real quick. We're going to start with a whole bunch of terminology. So I probably got 10 to 12 definitions for you today. And then the rest of the chapter is pretty much algebra stuff to get us ready for what we're doing next chapter. So chapter 3 is kind of a quick reprieve from everything we've been doing, and then we'll get back into the geometry after we finish this and after we come back to chapter 4. Okay, so first of all, we'll do some pattern recognition. So Patricia, let me ask you a question. What numbers come next?
It'll be like, okay, hold on. It'll be 18.
Nope. Want to try one more time? Okay. Wait.
21 and 34.
Why?
Because you add the two numbers which are like next to each other, so like 8 plus 13 equals 21, and then 13 plus 21 plus 34.
If we go back to the very beginning, we have 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, etc., etc. Do you know what that's called, by the way? Nobody? Okay. That's called the Fibonacci sequence. So notice what we did. I have a numerical system here, or a numerical pattern. The dot, dot, dot means it goes on forever. So I asked you for the next two numbers in the sequence. That's fine. And then I also asked you for the rule. The rule is frequently more important than the numbers. Recognizing what the pattern is that generates each of those numbers. Okay, should we try some more? Which letters are next in the sequence? Oh, number 2 stumps them already. Tom?
N and T.
Outstanding.
Thanks.
Why?
Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the first letter of every number.
Well done. Let's give it up for that one. That was good. Okay. How about this one? Nothing. Going once, going twice. Go ahead.
Is it like, does it go like 1/2 and then 2/3 and then 3/4? And then
What about the 0?
it just starts at 0.
Just start at 0. It's got to be a rule. You can't just randomly throw things in there. You're almost there. You just got to explain the 0 to me, and you're good to go.
0 over 1.
Good. 0 over 1, 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6. Those would be that. I wouldn't expect you to know that off the top of your head, but there they are. How'd you explain that? You know, like it's a quiz question. Now you've gotten the numbers. Now how would you write that out? Explain to me what you did to get what's the rule? Nothing? Okay, I just said fractions. Okay, that works for me. How about that one? Kira, tell me what thought process you're going through as you're trying to figure out this system. What are you trying?
I was trying to see what letters like you're skipping because
Okay.
they're like in order, they're in alphabetical order, but I was trying to see which letters you were skipping.
Good. So for instance, from A to E, I skipped B, C, and D.
Right.
So I skipped 3, but then E to F, I didn't skip any. Then F to H, I skipped E, F, G, H, 1. Okay, so that didn't work out. What can you try next? Well, we can do what Tom did. Do those stand for anything? Okay, so the one he did in the second one was 1, 2, 3, 4, 5. Could those letters stand for anything? Aardvark, elephant, ferret, hippopotamus, iguana, kangaroo, llama, mongoose? Probably not. Doesn't sound like a pattern there. Anything else? You're not gonna like this one. I'll tell you the answer. Strangely enough, the answers to this one are also N and T. So numerically it didn't work because we tried looking at how many letters were skipped. We don't really know any words that start with each of those things, so it's got to be something else. And a lot of times with these pattern recognition problems, that something else is something bizarre that you might not recognize. Look at all of those letters. What do they have in common? Or what don't they have? Grace?
Like a curve.
They're all the letters without curves. They're letters that can be made with segments. Okay, so we get into some bizarre examples here. Okay, let's do a couple more. How about this one? Oh, you already answered. Let's give somebody else a shot. Well, let's see if you're right first. Oh, hold on. Tell me what that number is, Tom.
16.
What do you got?
Then
Don't be biased by his answer. He could be wrong.
18.
So you agree it's 16.
Yes.
So you're probably both on the same track. Let's see what I got. I got 16, 18. Why? What's the rule?
They're not prime.
Yeah, they're not prime, also known as, what's the opposite of prime?
Composite.
Composite numbers. Okay, prime numbers not divisible by anything other than itself and 1. Those are the composite numbers. How about that one? You're not going to like this one either. And by the way, it's not 200. I didn't just add a 0 to 3 random numbers. Okay, it's got to be a recognizable pattern that starts from the very first number all the way to, and I don't know if a ... would be appropriate here because I think it ends eventually. Charlie?
I was about to guess 120, 150.
Nope. I'll tell you the answer, see if you can tell me the rule. This one's pretty cheap. Matt, you look like you got something. No? Should we give Tom a shot again? It's like the shell answer man today. All right, what do you got?
Okay. Well, like, I know my mom has one of them, but she has $1,000 bill, so could it be dollar bills or like money?
Oh, you're scaring me today. Denominations of U.S. money. Dollar bill, $2 bill, $5 bill, $10 bill, 20, 50, 100. There used to be a $500 and $1,000 bill.
That must have been lucky if someone dropped it on the street.
Yeah, well, the clue would be not to drop it on the street. Okay. Now, this one's different. What's different about this one?
Out of order.
They're non-numerical order. Good. What else? Doesn't go on forever. I don't have the ... at the end. So the question is, why are those numbers in that order? I will tell you, we could have added one more number at the back. I would have put a 0 at the back here. Nothing?
If you go from the outsides in, they go like down, so like 8 times 2 is 16, 5 times 3 is 14, or 15, 4 times 10 is 14.
Well, your 40 screws that up, doesn't it?
No, the 9 and 6 screwed up in mine.
Not a bad idea, though. Start playing with the manipulation of the numbers. You could also look at, like Kira said before, well, going from 8 to 5 is down 3. Then from 5 to 4 is down 1. Then, okay, and then that gets all screwed up. That doesn't work. I will tell you this, it has nothing to do with numbers. Nothing? I was hoping somebody would get this one. Those are the numbers 1 through 10 in numerical order.
Oh.
E, F, F, N, O, etc., etc. Okay. So a couple things to learn from this. Number one, the dot, 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 meaning it's a pattern that goes on forever. That's why I said I don't really know if there should be a dot, dot, dot here, because the number of denominations breaks down after a while. These, however, continue on forever. Without the dot, 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 it's what's called a finite sequence. It ends. And then your goal is to figure out why they're in that order, or why they are what they are. Okay, we can also look at something like this. Oh, wait, why did I? Oh, it's coming up, sorry. Couple terms for you. First of all, conjecture is an educated guess. There are two parts to that definition. Educated guess. Okay? So, if I was to say to Franny, hey Franny, how tall is my brother?
How tall are you?
Me? I'm 6'3".
6'1".
Is that an educated guess?
No.
Why not?
I'm guessing based off of how tall you are if he's your brother.
Let me ask my question again then. Is that an educated guess?
Yes.
Yes, because you're gathering information, which was how tall I am. You're generalizing that if I'm tall, there's a pretty good chance that my brother's tall. And you get, I forgot what you said for guess.
6'1".
6'1", not a bad guess. Okay.
How tall is he?
He's probably about 5'11". He's shorter, quite a bit shorter than I am. Okay. Alex, what color shirt is my aunt wearing today?
Red?
Red. Is that an educated guess?
Yeah.
Because?
My aunt's favorite color is red.
But it's my aunt we're talking about.
Well, I just.
Yeah, don't assume things. You know what happens when you assume things.
I can answer this question.
Which question? I've asked like.
Never mind.
Okay. Is that an educated guess?
And his color is
No.
No, we're just, you know, you have no idea who my aunt is, what color clothes she likes to wear, what mood she was in this morning, just a plain old guess. We're gearing, questions, sir?
What if you asked, like, what was your aunt's favorite color? Then would that be an education?
That would still just be a plain old guess, because he has no idea what color preferences my aunt. Now, if he had met my aunt, and she walked in blue jeans, a blue shirt, she had blue highlights in her hair, she was wearing blue shoes, she had blue socks on, she was wearing blue makeup, then that would be an educated guess. This whole process that we're using in geometry is called inductive reasoning. There are two schools of reasoning. One is inductive and one is deductive. We're using inductive. Sherlock Holmes, you all know who Sherlock Holmes is, right?
Yes,
Used
we will.
deductive. He went from general to specific. We're going from specific to general. We're taking a bunch of specific examples and eventually making a general encompassing statement that covers all kinds of different stuff. Okay? Billy is preparing toast for breakfast. After a few minutes, the bread popped but was not toasted. What conjectures can you make about why the bread was not toasted? Tom, we've heard enough out of you today. Matt?
It wasn't toasted long enough.
So it just didn't leave it. It was set too low. All right, good. All right.
He either put it on too low of a setting or forgot to plug it in.
Toaster's not plugged in. Now, I don't know about your toaster, but my toaster won't click down if it's not plugged in. I don't know why. Yeah. Anything else? What do you got?
It's broken.
What's broken, Billy or the toaster?
Billy.
The toaster's broken. Okay, good. What does the word, what do the letters P-O-S-T spell?
Post.
How about the letters M-O-S-T?
Most.
What do you put into a toaster?
Right.
Got a couple of you.
Toast.
No, you put bread into a toaster. It comes out as toast. Okay, now we go from a number or letter sequence to a visual pattern sequence. What's the next shape in the sequence? Draw it in your notes. Doesn't have to be perfect. We don't want that to happen. All right, everybody's got it, right? It's not rocket science. So we got 1 square, then we go 3 squares, and so you should have like a 4x4 kind of pyramid-y looking thing. Okay. What color is it? Charlie?
Green,
Why?
because we're going in the order of the colors of the rainbow.
Very good. Okay. So you've got to consider not only the shape of the figure, but also the color of that figure. All right. Counterexample. Counterexample is something that proves a statement false. So I asked Franny before how tall my brother was, and she said 6'1". My counterexample would be if I brought my brother in and you saw that he's 5'11", that would be a counterexample. Pretty much everything we do from this point on is talking about statements of whether they're true or false, or there's actually a third possibility, which we'll get to later. And the vocabulary associated with that. I gotta stand down because this clicker, it's not working. Oh, and I took that with me. All right. Both of those statements are false. Why? Simon.
If you insert 1 for x, 1 times 1 squared is 1, x is 1, 1 isn't greater than 1.
Perfect. Okay, so there's a counterexample for number 1. He said if x is 1, 1 squared is 1, which is not greater than 1, so counterexample. You got another counterexample for number 1?
0.
0. Got another one?
-1. No, scratch that.
-1.
Yeah.
-1 is not a counterexample. Anything else? There are more counterexamples.
Wait, for real numbers with fractions count as real numbers?
I don't know. Are fractions real numbers?
Yes.
Yes, they are.
What
Any
then?
number that we deal with is a real number.
But if a
But
fraction,
who knows? Huh?
if a fraction was squared, wouldn't it be like a smaller amount than x?
What fraction? 10/3?
No, like 1 over 2
1 over.
or 3 or 4.
What do you want? You're just gonna keep randomly.
A fraction that's less than 1.
For instance,
1/2.
1/2. Okay, is 1/2 a counterexample there? What's 1/2 squared? 1/4. Is 1/4 greater than 1/2? Nope. All right. What about the second one? Is that true or false? How do you know it's false?
As some little,
Huh?
as some get older.
No. It says both of the following statements are false. Okay? That's how we know it's false. I wasn't trying to be funny. I'm trying to get you to recognize what's going on in the problem. So what makes number 2 false?
Some die at the age.
No.
I think it's the platypus, but I could be wrong, but like there's one animal, yeah. it
Yeah,
lays eggs.
platypus. It's a mammal that lays eggs. It looks like a duck and a beaver. And fast fact for today, the bite of the platypus is poisonous. So you don't want to be petting a platypus.
Maybe be friendly platypus.
Bite you, it's dead. Hey, I got a quick video for you. I'm only going to play it once. Watch carefully. It's an old one. And it's very sad. Since we're talking about logic and reasoning, let me ask you a question. Whose fault is it that she fell down the trapdoor? Okay, hold on. We'll watch it once more, and then we'll talk about whose fault it is. So there are 4 possibilities. Her, the woman that opens the trapdoor, that guy, or the guy all the way to the left? Whose fault is it?
Hers because she didn't know what she was saying.
One could argue that it's her fault for not watching where the heck she's walking. Joanna,
The person who opened it?
the person who opened the trapdoor, because she pretty much opened a trapdoor to hell for that woman to just step right into. Okay? Tommy.
First, you decide to put a trapdoor in the middle of like the airway.
So you're going outside the possible 4 selections and choosing the construction guy. Okay?
And it could have been either of the other 2 people because they didn't tell her that there was.
Excellent. I think we've pretty much covered all the possibilities, right? So again, you can play now. I just broke it. Whoops. All right, let's go back. Come on. Try once more. It's not playing. Oh, bummer.
I felt like this came
All right, moving on then. I don't know why I won't play anymore. Okay, so now we're going to take all these statements that we've made and start using some logic. And some logic is a very structured process, meaning we're going to use something called if-then statements. If blah, 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 then blah, blah, blah. Okay? These are called conditionals. Because the second half is conditional on the first half being true. And the term conditional and if-then statements I will use interchangeably. Okay, so we'll start with this guy. If today is Monday, then yesterday was the weekend. We're not going to talk about true or false yet. That comes later in the slideshow. Right now we're just getting some definitions under control. Okay, so you see why it's called an if-then statement. It starts with an if, then there's a comma, and a then. Okay. The first part, the if part, is called the hypothesis. And the then part is called the conclusion. One of the problems in this lesson is there are a lot of terms that begin with C-O-N. You got to keep all of those straight. Conditional, conclusion. Just for giggles, is that a true statement? No?
Yeah.
Okay, good. We're split on that one. We can argue about that later. Because we're dealing with a lot of different terminology, and we're mathematicians, we know that as mathematicians we're lazy, and so we start to create notation and shortcuts to write everything out. So one of the first things we do is instead of writing out a big long sentence like, if today is Monday, then tomorrow, or yesterday was the weekend, we started using letters like P and Q to represent the hypothesis and the conclusion. Okay, we can also use this notation. The arrow means implies. So this means P implies Q. Now, what P is and what Q are up for discussion. And that's depending on the problem that we're working on. Okay, so for instance, I could rewrite that last statement as Monday implies yesterday weekend. It's not the best English in the world, but it gets the job done. You're going to have to be able to switch back and forth between different, the way sentences are structured. So for instance, if I have something that says, all cows moo, then I'd like to be able to write that in if-then form. So you have to figure out what am I starting with and what am I ending with. So for this one, it's pretty straightforward. Am I starting with a cow or am I starting with mooing? What's happening first?
Cow.
Starting with a cow. And if I have a cow, then that cow has to moo. So we can convert that into if something is a cow, then it moos. Or if you prefer, a cow implies moo. Does that make sense? Yes or no?
Yes.
Okay, good. You have to be careful with what you start with. Remember, in this case, we're starting with cows and we're getting moos. You may have to also go from if-then form to this all form. And again, this You have to be able to identify what we're starting with, because it will change depending on the problem. Okay, now things get weird. So if we have a statement P implies Q, we can switch the order. So instead of doing P implies Q, we get Q implies P. That's called the converse. The if statement becomes the then statement becomes the if statement. So if we take that first one, we would switch it. If yesterday was the weekend, then today is Monday. I think I have the cow one in here too. Yeah, if something moves, then it is a cow. Is this true?
No.
No. How about this one?
No.
No, why not?
I can move.
You can move.
I'm a human.
Uh-huh. You're not a cow.
No.
Good.
Or it's a cow in disguise.
Inverse. Now, instead of just switching the order, we're not going to switch the order at all. We're going to do what's called negating each of those things. That's what the little tilde means. It means putting a not in front of it. Okay. I am happy. I'm not happy. I'm not happy. I'm happy. It's the opposite of what we're talking about. If something is not a cow, then it does not move. Another sidebar, what's that a picture of?
A bull.
No. No.
A male cow.
No. No.
Buffalo.
No.
Bison.
No.
A cow.
No.
Picture of a cow.
Oh.
I don't know what it
It's a picture of a cow. Beef.
Ground beef.
Uh,
Cow with no legs. Ground beef. Yeah. I'll be a little slow on that one, but we'll get on. All right, then the contrapositive. Contrapositive is a converse and an inverse, so we're going to switch the order and negate them. Again, switch the order and negate them. You all understood that ground beef joke, right?
Yeah,
Okay, good.
because it's on the ground because it has no legs.
There you go. Good.
what does the thing mean again? The little circle.
The tilde
Yeah.
means not,
Okay.
or the opposite of. So if I was to say to you, Joanna, what do you do with the dog with no legs? What do you do with the dog with no legs? Huh? What do you do with a dog with no legs? Take it for a drag.
That's horrible.
Oh wait, it's gonna get worse. Here's part 2. What do you name a dog with no legs? You don't, because it won't come when you call it.
Oh
How are we doing so far? You want the worst one?
Yeah, let's hear
I
it.
got one.
Let's hear it.
What do you name a dog with no legs and steel testicles?
What?
What?
Sparky. Get all those?
I have
Got it?
one.
Okay, good. No, it's not joke telling time. Put your hand out. If something does not move, then it is not a cow. So again, you switch the order, negate both of the terms. You can see when we start talking about truthness and falseness, if those are even real words, this can get fairly confusing. So you have to visualize something that doesn't move, and then you have to ask yourself, well, if that thing that doesn't move, like a chair, that chair doesn't move, is that not a cow? Yeah. I think so, yeah. It gets confusing, but I have some theorems later that will help you figure that out. Okay, so here's our example. If you live in Mount Prospect, then you live in Illinois. Is that a true statement, Matt?
No, because there could be other Mount prospects in the world.
Okay, so thank you, Matt. That makes for a good segue. We're going to assume that certain things are true. Like, for instance, yeah, there's probably some cow out there that had a freaky vocal cord accident and can't move. Or there might be a dog out there that only has 2 legs. Or no legs.
My sister.
So, Matt, you might be right. There might be another Mount Prospect somewhere, but we're going to assume that that's the Mount Prospect that we're all familiar with. So, is that a true statement, Matt?
Yes.
Good. What's the converse of that statement, Matt?
If you live in Illinois, then you live in Mount Prospect.
Beautiful. Is that a true statement?
No.
What would be your counterexample, Matt?
If you do not live in Mount Prospect, then you do not live in Illinois.
Okay, when we do the counterexamples, they don't have to be written in sentence form. It's just an example. So where would you have to live in order for that converse to be false? Matt,
Anywhere but Mount Prospect?
for instance,
I don't know.
you can't name another city other than Mount Prospect?
Romeoville.
Romeoville, excellent. I don't know where that came from. I was thinking you'd say like Arlington Heights or Schaumburg or.
Springfield.
You went right for Romeoville. I have no
Wait,
idea.
that's a
I
place?
think it's way south. All right, Matt, what's the
Yeah.
inverse of that statement?
Give me a second. Can I get some help on this one?
Well, what does your definition say? What do you do for the inverse?
Converse. There's a converse.
Christian, what do you got? What's the inverse?
I don't have a definition for inverse.
Take a nap. Madeline, what do you got?
If you don't live in Mount Prospect, then you don't live in Illinois.
True or false?
False.
False. What's your counterexample? Yeah, it gets confusing, doesn't it?
Well, you can live in other places in Illinois.
Like, for instance,
Romeo.
Romeo, China. Okay, good. Matt, back to you. What's the what's the contrapositive?
Switch order and negate them. So you switch the order and negate them. So if you do not live in Illinois, you do not live in Mount Prospect.
Perfect. True or false?
True. True.
It is actually true. All right, now, the weird thing is, it would seem that the true and false are the only possibilities. There's actually a third case, which is called CBD, cannot be determined. Our if-then statement has a hypothesis. It's called an if-then statement or a conditional statement because the second part of the statement is dependent on the first part. So in other words, you have to have the hypothesis true before we can move on to the conclusion. Okay. So here are three examples. If something is a cow, then it moves. We have two cows there. Okay. We have to have a cow first, then it has to move. Can you have a cow? Yes. Therefore, it must move. If something swims, then it's a fish. Can you find something that swims?
Yes.
Yes. Is it a fish? No. Could be
Human.
dolphin, whatever. Here's the third case. If the moon is made of cheese, then Mr. Reedy eats glass.
What?
Do I eat glass?
I don't know. Maybe.
Okay, and this is the important thing. There is no answer to that. It cannot be determined because according to this statement, you only know if I eat glass if the moon is made of cheese. And last time I checked, the moon is not made of cheese. Okay? So we call that a true statement, a true-false statement, a false nothing statement. Question?
Wait, how is the first one true? Because can't like somebody move and not move?
Ask yourself the question, what are we starting with? We're starting with a cow. So if you have a cow, does it move? You're thinking about the converse there. You're starting with something that moves and wondering if it's a cow.
Oh.
And we've
okay.
established that that's not true because Tom can move,
Okay.
which sounds like a Dr. Seuss story. Tom can move, can you? Isn't there a Mr. Brown can move? So, is that it? Mr. Brown can move, can you? Something like that? You guys not know who Dr. Seuss is?
Yeah. Child one guy that made
Child.
it.
What's that?
Didn't like hate children.
No, I think that was Lewis Carroll. I don't know. I'll
Pretty sure he hated
think so. Okay. I'll look it up. The Google will tell me. Okay, so we can get to this, and this will help with the weirdness of the inverse and the contrapositive as to whether or not they're true. If the conditional is true, then the contrapositive is true. If the conditional is false, then the contrapositive is false. So you should never have to think about whether or not the contrapositive is true or false. You just have to go back to the original statement. And so when we talked about Mount Prospect and Illinois, I could see Matt trying to figure out the contrapositive and doing all that other. You just go back to the original statement. If the original statement was true, then the contrapositive is true. The same relationship occurs between the converse and the inverse. Converse and inverse are always true, true, or false, false. Okay, so the conditional and the contrapositive are linked. The converse and the inverse are linked. Time's the bell ring? Quarter? Right? Quarter after?
Yeah.
Okay, we're doing okay. You got this? If an animal is a bat, then it can fly. Emily, true or false?
True.
Which one? True, right. Again, there's probably a bat that got its wing caught in a weed whacker and just runs in circles. But in general, bats can fly. Good. What's the converse, Emily?
If an animal.
Yeah.
Yeah. If an animal can fly, then it's a bat.
True or false? False. Counterexample?
Birds can fly.
Other birds, yeah, other birds like bats are birds. I mean, yeah, I slept through biology. Birds are a counterexample because they're animals that can fly. Okay, how about the inverse?
If an animal is not a bat, then it can't fly.
Good. True or false?
False.
Because?
Birds can fly.
Even easier. Okay. Why is this false? Because of the theorem we just learned, and we know that the converse is false, then the inverse must be false because these two are linked to each other. Okay, everybody follow that idea? All right, coming up with a counterexample might be a little trickier, but as far as establishing truthness and falseness, again I'm making up words, link the converse and the inverse together. All right, and last but not least, what's the contrapositive, Emily?
If an animal can't fly, then it's not a bat.
Good, true or false? Don't think.
False. True.
True, why?
Because the first one is true.
Good, because the original statement is true. So this will make the decisions on the inverse and contrapositive a lot easier if you remember those theorems. Okay? We got it? A lot of terminology today, and you got to be able to sort all that out. Fast fact for today, by the way, is that a baby bat is called a pup. So feel free to use that at the dinner table tonight if you like. Yeah, look at how cute they are. Until they bite you and you get rabies. You have to give like 8 shots in your stomach to get rid of it.
saw that one.
I say bat all the time.
Yeah.
Because of Batman?
No, just because I've seen bats before. Okay, we good? What?
What do you call a dog that has a
So
suntan?
you're gonna tell the joke anyway.
Oh, what?
A hot dog.
Wow. Wow. I have no response.